Welcome back to lecture number 8, where we'll be looking at Z transforms in the course EEE 4221, Digital Signal Processing, one of the courses at 4th year at the University of Zambia. My name is Dr. Charles S. Lubovia, and the lecture outline will run as follows. I'll give a brief introduction, and then I'll talk about the definition of Z transforms. Thirdly, I'll give examples, and then we'll also look at poles and zeros. And then this will lead us to transfer function of Z transform functions, and then we'll look at finally how to determine system stability, in the Z domain. So with these subsections of our lecture for today, let's begin by a word of introduction. Z transforms are a powerful tool to use in the analysis and synthesis of discrete signals. You recall in the course EEE, is it 3221, Signals and Systems, one of the courses here at the University of Zambia at 3rd year. You will recall that when we were discussing continuous time signals, we were analyzing them using Laplace transform. But when it comes to discrete time signals, it's best to analyze them using a tool of Z transforms. And therefore, we'll find this tool very useful in the analysis of digital filters, in the analysis of difference equations, in the analysis of even a convolution of two signals in the digital domain. So having said that, let's now move straight and look at the definition of Z transform. Now, given the discrete signal x of n, we can actually define Z transform x of z. Take note, I'm using capital letter X here as opposed to small letter here. This is in the time domain, and then that becomes the Z domain. So you are basically transforming a signal from the time domain to the Z domain. That's what we call Z transforms basically. And by definition, X of Z is nothing but the summation n from n equals 0 to infinite of the product of the discrete signal x of n being multiplied by z to the power minus n. Again, here n ranges from 0 to infinite. So let me call this one equation 1 in the definition. We can then expand equation 1 to form a second equation, which is the expanded format of equation 1. This is basically x of 0, z to the power minus 0 here, plus x of 1, z to the power minus 1, plus x of 2, z to the power minus 2, and this goes on. Let me call this one equation 2. So basically what you are seeing in the expansion is I take at x, when I substitute n equals to 0, then I'll have x equal x of 0, and here where I have z to the power minus n, I put a 0 here, I have the first term. Plus, since this is a summer, I put now n equals 1, so x of n, multiply by z to the power minus, where this n now again I put 1, I get the second term, and I can do the same to the third term until I reach infinity. So basically you notice that the x values are changing from 0 all the way to infinite. I mean the n values are changing from 0 to infinite. So equation 1 and 2 are basically the basis for the definition of Z transform. It's what defines Z transforms. Having defined what Z transforms are, let's now give examples. And my examples will range from any discrete sequence up to exponential and trigonometric functions. So let's look at the first part where you are given any sequence of numbers for x of n. If you are given any sequence of numbers for x of n and you are asked to find the Z transform, and here let's do an example. Suppose x of n is given as 1, 2, 3, and 4. And then you are asked to find the Z transform. Find the Z transform of this sequence. So what you do is go back to the definition of what Z transforms are. We defined Z transform as x of z summation n equals 0 to infinite x of n z to the power minus n. So from equation 1, or from this equation here, we can again do the expansion, noting that in the sequence this is at position 0, this one is at position 1, the 3 is at position 2, this one, the last sequence numbers here is at position 3. So noting that and expanding here, we are going to have x of 0, z to the power minus 0, plus x1, z to the power minus 1, plus x of 2, z to the power minus 2, plus x of 3, z to the power minus 3. So the next step now is to just substitute your x of 0, which is basically this one, and the x of 1, which is your 2, and the x of 2, which is your 3 here, and the x of 3, which is your 4. So you're going to have 1 z to the power minus 0 plus 2x z to the power minus 1 plus 3z to the power minus 2 plus 4z to the power minus 3. Now, we know that this part here can also be written as 1 over z to the power 0, and z to any number to the power 0 is simply a 1. So the first term therefore reduces to nothing but simply 1 plus 2z to the power minus 1, 3z to the power minus 2 plus 4z to the power minus 3 as your final answer. So, what are we noting here? We can easily find the Z transform of any sequence of x of n from the definition by simply expanding this into this format and then substituting whatever sequence that you are given and then simplifying that sequence until you find the final answer. That's example number 1. Let's move on now to the second example. In the second example, I want us to find, how we can find the Z transform of the impulse or delta function. Now, from the definition, we know that a delta function can be defined as delta of n is as being equal to 1 at n equals 0 and 0 otherwise. That's the definition of a delta function. It will have the value of 1 at n equals to 0, and it will have the values of zeros at any other point besides n equals 0. So here the value is 1, but at any instance it will be 0. So from the definition, since we know that dn now is equal to 1 at n equals to 0, how then do we find the z transform of such a function? Z transform is given by, you can actually denote it as d of z as being equal to summation n equals to 0 d of n z to the power minus n. So simplifying this, we'll notice that at d n of 0, z to the power minus 0, there is a value, and then at dn of 1, z to the power 1 plus dn of 2, z to the power minus 2. This can be simplified to, at dn of 0, the value is 1, and then this is simply z over 0 plus at d of n, at d of 1, it's 0 to the power z minus 1, and also at d of 2, it's also 0 with a delay of 2, and this keeps on giving you zeros at any other value beyond 1 up to infinity. You get 0. So simplifying this part, you get 0. This whole part is 0. This part gives you 1 over 1, which is simply 1 plus 0, and so on. Therefore, the final answer is simply 1. So the z transform of an impulse or delta function will always be 1. Let's move on to the second one. The next example, rather. Now look at the unit step function. Example number 3. Unit step function. Unit step function. Unit step function is always written in terms of its ua of n, small letter ua of n, and this function will have the value of 1 from n equals 0 to infinity. So all these values here, the sequence will look like this. Okay, so basically if you are to draw it, this will be a function of this nature up to infinity here. At whatever value here, it will have the value of 1, and it can be sketched as follows. So basically, by definition, a unit function will give a value of 1 for n equals 0. From n equals 0 to infinity, and then 0 otherwise. Okay, so having noted that, so we can now find the z transform, capital U of z, as opposed to small letter u of n in the time domain, in the Z domain, you make sure this is capital letter Z. So from the definition, this again will be equal to n of 0, n equals 0, a summation from 0 to infinite, u of n, z to the power minus n. Okay, so what that means is that we have said that this will be now u of 0, z to the power 0, plus u of 1, z to the power 1, plus u of 2, z to the power minus 2, plus u of 3, z to the power minus 3. This goes on up to infinite. Now, we can simplify this to have 1 over z to the power 0 plus 1 over z to the power 1 plus 1 over z to the power 2 plus 1 over z to the power 3, and this goes on. Now, from this equation, u of z, you recall when we were learning about geometric series, we had the function a plus a1 r to the power 1 plus a2 to the r to the power 2 plus a3 r to the power 3, and so on. This in geometric series can be simplified as nothing but 1 over a minus r, where r in this case should be less than 1, or r, the magnitude of r should be less than 1, and r must range from -1, or r must be greater than -1 but less than +1. So in this case, when it comes to Z transform, this becomes the 1 over Z part. Then this part will simply be the unit function A. Therefore, we can simplify this series as follows. Okay, so applying theories in geometric series, the unit step function Z transform can be simplified to 1 over 1 minus 1 over Z, which if we multiply Z both in the numerator and the denominator, this will be Z minus 1. This is known as, this equation here is a very important equation. It defines what is known as the closed form of Z transform for a unit step function. So it will always be Z minus 1, because we have basically simplified this by multiplying by Z here, by Z here, by Z here, and so we get the transfer function, we get the Z transform of a unit step function as reducing to Z divided by Z minus 1. Let's move on to the next example. Example number 4 will have to do with the exponential function. If we are given x of n as being equal to theta n, this is an exponential function, and we are asked to find the Z transform, and this is given with reference to the unit step function. Okay, so if the function x of n equals e exponent theta n with reference to a unit function, and we asked to find the z transform of this function, so x of z will be given by 1 over 1 minus 1 over z. Okay, but then we have said that this is the same as z minus 1 in terms of a unit step function. But because we are finding the one for the exponential function, we can then multiply this part by the exponent. This gives us 1 minus e to the power theta n 1 over z, and then when we multiply everything there, that will give us z 1 minus e to the power theta n. Either in this format or in that format. This format can also be written as 1 minus e theta n, and then this will be z to the power minus 1. So either you get it in this format or you put it in this format, z over z minus theta. So that's about the exponential function. Finally, I want to give an example to do with a trigonometric function. Let's do an example with a trigonometric function. Suppose you have a trig function. Suppose you have x of n equals r to the power n cos theta n. And this again, is with reference to the unit step function. So to find the z transform of this, all you need to do is, first of all, factor out r of n. You recall when we were learning about Euler's formulas, we did mention that the cosine function can be written as e to the power theta n plus e to the power minus theta n divided by 2, where again there must be a j component in the equation there. So that's the cosine equivalent. So that part here is the same as that. Now this is again with reference to a unit step function. We can then expand this. The way to break it, this is the same as r to the power n e to the power j theta n divided by 2 plus e minus j theta n divided by 2. Everything else is with reference to the unit step function. And then Rn can be multiplied by each of these to get j theta n divided by 2 plus Rn r to the power n e minus j theta n divided by 2. But again, each one of these must be with reference to a unit step function. So simplifying this further, I can rewrite this x of z being equal to r to the power n j theta n divided by 2 with reference to the unit. I multiply the unit by each of the two terms plus r to the power n minus j theta n divided by 2 with reference to the unit. You can actually reduce this to that format, or from here you can just apply tables of z transforms, and that will give you straight to that equation, and you will have resolved a trig function in terms of the z transform. So having analyzed this, we can simplify any z transform in terms of poles and zeros, and then determine system stability. If y of z is a z transform of a function that has a input x of z Okay, x of z, say 1 plus whatever function you have here. Then the transfer function will be nothing but y of z divided by x of z equals to whatever function you are given there. So the transfer function is nothing but the ratio of the output to the input. So if I know the z transform of the input, I know the z transform of the output. The ratio of the output to the input gives me the transfer function. And this transfer function will have what are known as poles and zeros, whereby if this is A naught, maybe this is z minus any 0 here, z1, again z minus z2, and then for the denominator b0 you may have again z minus pole 1, and then you may have also z plus pole 2. So if I equate the numerator, each of these to 0, then I'm going to have z minus z1 equals 0. Then my z is equal to whatever pole I have here, which is 0, 1. Then this becomes a 0. When I equate each of these to 0, what I would get will be pole 1, z equals pole 1, z equals pole 2, and so on and so forth. So you notice that from the transfer function, you have the numerators consisting of zeros and the denominators consisting of some poles. These poles and zeros is basically what determines stability. This leads us to what is known as the pole zero plot in the z domain or z plane. You can plot these poles and zeros in the z plane, and this will form what is known as a unit circle, where this is positive 1, minus 1, minus 1, positive 1. So within this circle here, if the poles falls inside the unit circle, we say the system is stable. It doesn't matter, the zeros may be here, the position of zeros doesn't determine system stability. What determines system stability are the positions of the poles. When the poles are inside here, the system is stable, or they can be here, or they can be here, or they can be here, we say the system is stable. But if the poles, are right at the boundary, we say the system is marginally stable. Poles, when poles are at the boundary. Okay, that's number 2. When they are inside the unit circle, we say it is actually, the system is stable. The third scenario is when the poles are outside the unit circle. The unit circle, then we say the system is unstable. Okay. Again, there may be another scenario where you may have 2 poles at the boundary, one here and another one there. At the same point, we still say when that happens, we say the system is unstable as well. So, for the system to be unstable, either poles are outside the unit circle, or you have 2 poles appearing at the same point on the boundary of the unit circle. We say the system is said to be unstable. So this stability the plot will become critical when we look at the next lecture, which will be lecture number 9, where we'll be talking about digital filters, especially when we come to the infinite impulse response filter, because it is that type of filter that will consist of poles and zeros. And it's important to notice that once you calculate your transfer function, analyze the poles and the zeros, and if those poles are inside the unit circle like this, then we say that filter is stable. But when they are outside, or two poles are appearing at the boundary, then we say that filter will be unstable. So this lecture on Z transform forms a very good foundation in the understanding of digital filters, in the understanding of difference equations, in the understanding of convolution of discrete signals, and it will be very key even as we apply the next lecture, which will be lecture number 9.